Let me do two examples using those prefixes that we talked about at the end of last time, because there's a few problems you have to do like that coming up. Prefixes. It might actually be prefixes. That's how X's usually work with. So let's say that we have 600 microseconds, and we want to express that in seconds. Well, just what I gave you at the end of class last time was this list that said you can think of the micro as meaning 1 times 10 to the minus 6. Okay, and so if you're starting with 600 microseconds, you can just replace the micro in there with times 10 to the minus 6. And so 600, replace the micro with times 10 to the minus 6 in each seconds. And then that comes out to be, well, we have, so first 600 times 10 to the minus 6 seconds. That's not really scientific notation because we have more than one leading digit. So if you want to go from this to scientific notation, well, what do you have to do to, so let's break this up into two pieces. There's a part before the times and a part after the times. What do you have to do to the 600 to make one leading digit? What do you have to multiply or divide it by? You have to divide by 100 to make that 6. You don't want to change, dividing this by 100 though, changes the whole value. We don't want that. So if you divide this part by 100, you have to multiply this part by 100. Okay, so to get this in scientific notation, divide this by 100 makes that 6.00. Multiply this by 100 makes that 10 to the minus 4. And then you have the answer in scientific notation. So 6.00 times 10 to the minus 4 seconds. So I think that's sort of the easier way. If you're trying to go from something with a prefix to something without a prefix, you can just make that substitution. The other way that you can go is say you have 40 kilograms. No, 40. Let's say we have 40 grams, and we want to convert that to kilograms. Okay. So this is the opposite of what we did before. We have something with no prefix, and we want to go to something with a prefix. So to do that, you have to recognize that there's this equivalence between, 1 kilogram is equal to how many grams? Well, 1,000. Yep, you can just replace that prefix with the number. That's 1 times 10 to the 3rd grams. And then you can just do it like a unit conversion. So if we're starting with 40 grams, for the unit conversion, we want the ratio with grams in the denominator to cancel this one. So we have 1 times 10 to the 3rd grams there, 1 kilogram there. The grams cancel. And you get 40 times 10 to the minus third kilograms. So those are the two ways you can go. You know, you can go from something with a prefix to something without, and something without to something with. Okay. And you can go from something with a prefix to a totally different prefix, different units or whatever, by just combining these two. To put this in scientific notation, what do you have to multiply or divide the 40 by to give one leading digit? Divide by 10. That means you have to multiply this by 10. So we have 4.0 times 10 to the minus second kilograms. Any questions about that one? Okay. So now we're going to start talking about kind of our first physics topic. These are just sort of preliminary. Yeah. 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 I don't know. Yeah. Yeah, I think so. I just don't really. You can round to whatever you want. I'm not going to worry about significant figures. Yeah, because I sort of don't want to take class time to go through like all the rules and stuff, you know. So, yeah. But don't do that in your chemistry classes. They'll get super mad. Yeah, yeah. Don't tell your chemistry. This is even more important. Don't tell them that I don't make you do it. Okay. So now, any other questions? So now we're going on to kinematics of a particle in 1D. And we have to break all this down because this is 3 new terms. First of all, kinematics is, we're making a distinction between kinematics and kinetics. Those are 2 different things with, like, why would you, the person who invented this, like, they could have picked any 2 words they wanted. They picked 2 that sound virtually identical, just out of spite. It makes no sense, but I didn't get to choose. It was way before me. But here's what they mean. Kinematics means you're describing motion. And you're not dealing with any of the causes of the motion. You could also think of it as all stuff that you could figure out from watching a detailed videotape of something. You know, you could tell how fast excuse me. You could tell how fast something's moving. You could tell how far it moves this way or that way. You could tell how long it takes to get from here to there. But you can't tell anything about the mass of the thing that you're investigating. It could be hollow or something, you don't know. And you can't tell anything about the forces that are being applied. So no causes, no mass, and no force. This is stuff you can figure out from video. Kinetics combines kinematics with the causes. And those causes are force and mass. So we're gonna, we're gonna start out with kinematics because it's the simpler one. You're just describing the motion, and then we're gonna add kinetics. And I need a new memory device for this. I didn't used to think about it at all, and recently I feel sort of guilty about describing it this way, but I still think it helps you remember it. So anyways, here it is. I don't mean, nobody should take this personally, but it occurred to me that this is the simple one, this is the hard one. And so kinematics is the one that's simple enough for your ma to understand. It's like insulting, a little bit sexist. I never thought about that. I don't mean it like that, but it's just a way to remember what's easy and what's hard. And that helps you remember what's, okay. No offense to your mom. I'm sure she's very nice. So we're on kinematics. Later we'll do kinetics. And the next thing we have to describe is what's a particle. A particle is something that has no length dimensions. It can have mass. So let's say it can have mass, but it's treated as having no length dimensions. So we treat it like it has the size of a point. And since it has no length dimensions, you can't make any distinctions about what's, if it doesn't have any length dimensions, there's no this part and this part of it. Everything just happens in one location. So you can't make a distinction between the left and the right or the top and the bottom. And therefore, you can't deal with orientations if you're dealing with something as a particle. Let's make this a comma. So there's no orientation. There's only the location of that little thing. So you can track where it moves around the room, but you can't figure out if it's upside down or turned around this way. And so later we'll get into approximating things as rigid bodies, and those can have length dimensions, and that'll lead to some other calculations we have to do, but it'll give us the ability to determine whether something's going to end up upside down or this way, or how fast it's spinning and that kind of thing. But we don't have any of that with a particle. Okay, so what objects are reasonably represented as particles? You might think something really small for one thing, but that doesn't, and that's a reasonable thought, but everything's relative, like an atom is gigantic compared to a subatomic particle, and an atom is pretty small, so like where do you make this cutoff? Well, really what it has to do with is there's no absolute thing that we treat as a particle, or that always you would want to treat as a particle. It's just a matter of what information you want to get out of the thing. So, for example, when people are doing calculations about planetary motion, they usually treat the planets as particles. Planets are gigantic, but if all you care about is where that planet's location is going to be, and you don't care about its orientation, that doesn't come into, its orientation, say, doesn't affect its gravitational pull at all. So there's a lot of cases where you don't care, it's not worth the extra work to figure out what the orientation of the planet's going to be. You just want to know the location of the middle of it. And so you treat a planet as a particle, you know. If there are times, like in this class, there'll be times where we treat a car as a particle, you know, because in the calculations we're doing, we're just going to be trying to figure out the location of the car after this stuff happens to it. But obviously there are other applications where it's really important doing calculations involving cars to know whether it's going to be upside down or right side up, you know, like, yeah. Yeah. So I don't know if I said this only to I might have only said this to the day class, but I am not a real physicist. Okay, I'm an engineer, so that's a disclaimer. But light has, I guess, that one I think I can sort of answer. Light it's a thing that is neither a wave or a particle. It's its own thing. And that own thing has properties of being a wave and being a particle. And depending on how you look at it, you see those properties. You know what I mean? And so, yeah, so I think I think a real physicist would say that that since we're only used to dealing with things that are either waves or particles, we're sort of unprepared to accept the idea of something that has all of these properties in one thing. And so to us, it depends on the application, you know. Okay, so a particle is not there's nothing that's inherently a particle. It's just it's an approximation we make so we can do the math. And then the last thing we have to talk about, define, is one dimension. 1D means that at any location, an object only has two choices of which way to go. At any instant, only has two directions to choose from. So that includes trains on train tracks. You know, a train on a train track can only go forward or backwards wherever it is. That includes things traveling along a wire path. It includes anything that's confined to a line or any kind of curved defined path. It doesn't include things, you know, something that can travel around the whiteboard is in two-dimensional motion because so this thing here could go this way, or infinitely many other directions from there, you know. Something so this is a particle that is in one-dimensional motion. If it's here, it can only go this direction along that path or this direction along that path. And the nice thing about 1D is nice because since at any instant there are only two possible directions it can go, that's exactly the same number as signs. You know, there's a positive and a negative. So let's say its two directions can be represented by positive and negative. And we'll see when we get to 2 dimensions, and it's also true in 3 dimensions. This particle here, that has infinitely many directions it can go, there's still only one positive and one negative. So that's not going to work for describing directions here. We're going to need something more complicated to define directions. So when we go to 2D and 3D, we have to go from talking about numbers that just have plus and minus to tell directions to these complicated things called vectors. And so let's say when you move up to 2D, you need vectors to describe the direction. Okay, so this first topic, we're still, it's been like 10 minutes and we're still as far as the title of this section. We're talking about describing the motions only of things that we're treating as having no length dimensions, so we don't care about orientation, and they're traveling along a confined path where they can only go forward or backwards. Okay? And in order to put numbers to a particle as it moves around, what we'll mainly want to do is we'll want to describe the object's location numerically in relation to time. So we'll want a number that defines its position a number that defines the time, and say that this number defining the position, we're going to call that p, lowercase p. The number defining time is going to be lowercase t. And we want the position to be a function of time. Okay, so you've dealt with functions where, like, well, let's give an example. You might have the position of an object equal to 5t squared, all t greater than 0. This is what we're always going to try to get, is some mathematical relationship that says, okay, what's the position of the object when time is equal to 0? Well, we just have this function, so plug 0 in for t, and you get that the position is also 0. What's the position when t is equal to 5? 5 squared is 25, times 5 is 125, so the position is 125. Okay. That's the relationship that we're going to want to have. But before we can do that, I have to talk about what it means to put a numeric value on a position or on a time. So take a couple minutes doing that. Anybody have any questions that pop in your head yet? Okay, so in 1D, in order to assign a numeric value to position, you need to choose two things. And those are, first, some reference point, some physical point in the path of this object that you're going to call 0, that you're going to call 0 position. So a location corresponding to position 0. And the second thing you have to choose is, so the object in 1D always has two directions it can go. You have to assign one of those directions positive and assign the other direction negative. So a direction corresponding to positive. Once you choose which direction is positive, then the other direction is negative. Okay, so let's see what this looks like. So let's think about a one-dimensional motion. So that's here's the train. I only know how to draw steam trains. This works as well for more modern trains. The key is the cow catcher thing. Okay. So let's say that we're doing all of our length measurements in meters. Okay. So we know that we already have a distance defined. Meters are already, we know what a meter is. But how do we figure out the location of this train at this instant? Let me do one more thing. Let's say, so we're treating the train like a particle. So we can't have any length dimensions, which means we have to have the train represented by a single location, a single point in space. The center of mass of the train. So that symbol is center of mass. So let's say that's what we're tracking. Okay, so what's the location of that? Is it like 100 meters or is it -5 meters or whatever? Before we can assign a number to that location, we have to choose those two things. So let's say that we've decided that this is what we're going to call our 0 position. I'll write capital O, scripty O for origin. And then we have to choose which direction is positive, and that's arbitrary, just like our choice of the 0 position is arbitrary. So let's say going along the tracks this way is positive. And now we can use a meter stick and measure how far we are from the 0 position. Let's say, so there's 1 meter, 2, 3, 4, 5. Okay. So the train is 5 meters in the negative direction from that 0, from the origin. And so if something's 5 meters, or just talking mathematically, if something's 5 in the negative direction from 0, what's the number associated with it? Yeah, so the position at this instant is -5. Okay. So notice that all of these numbers that we're going to use to define the locations of things is dependent on these two arbitrary choices we make at the beginning. Okay. We could have just as easily put the 0 position back here, and then this would have been +30 or something. But the key is that we're going to choose our 0, choose our positive direction, and then the whole rest of whatever problem we're working on is going to use that same numbering system. And it's going to let us do calculations.
Is there a reason that you chose for it to be a -5?
Just because I just wanted to show what happens, like how negatives come up, but not really, If you wanted to plot this, you could plot this position on a number line. And that'll come up a little bit more today. So if this is your number line, this is your 0, 1, 2, 3, 4, 5. So that's the position. In order to come up with, so remember our goal is we want to represent the position as a function of time. But we also need to assign numbers to times. So now to assign a numeric value, value to an instant in time, you need to choose an instant in time that we're going to call 0. Okay. So you need to choose, and again, this is arbitrary, an instant corresponding to 0 time. You don't have to choose a direction for time. It's the same idea as choosing a 0 for position. For time, you don't have to choose a direction because we only deal with time moving forward. Direction you can think of is already chosen for you. Yeah, mathematically you totally could, but people don't, and we're not going to. So yes, that's there's really no mathematical reason. Like, we're never going to deal with negative times, and there's no mathematical reason for that, but we're not going to. And just that's how people sort of all do it. So that's what I'm going to do too. So once you choose a 0 time, let's say that we decided to call time equals 0 8 seconds before this picture right here. Okay. Then once you choose that 0 time, you can use a stopwatch or whatever. That's 0 is when you click on the stopwatch, and now every event that happens corresponds to a number time. Okay. So compared to this 0 time, every event in a problem occurs at some later positive time value. Okay, let's say, for example, let's say the picture above happened at t equals 8 seconds. Then you could write the position as a function of time at that location, like this. Then the position I want to do this. Position as a function of time is equal to the position at time 8, and that's equal to -5. Okay, that's using mathematical language of functions to describe what's going on. But the idea is exactly the same as the way you're used to dealing with locations and times. Like if somebody asks you what time it is, you say it's 1:15 because noon or whatever is a reference point that the hour and 15 extends after. You wouldn't say 1,000 minutes or something. It's 1,000 minutes from something, but if the other person doesn't know what reference you're referring to, it doesn't do any good. And same with position. You wouldn't, like if somebody asks you where you are, where the restaurant is or whatever, you say it's 2 blocks north of, some other location. You need that reference location and you need the direction. Okay. This is using exactly that same stuff. It's just putting it into a mathematical, language. Okay, so now that we have the time and position at this instant, you can plot it on a position versus time graph. So if this is our coordinate system, this is time, and this is position, to plot this this event on a position versus time graph, we go out to positive 8 seconds. 1, 2, 3, 4, 5, 6, 7, 8. This is in seconds. The position's in meters. And we know that at 8 seconds, the position is at -1, 2, 3, 4, 5. And that point on the graph represents what's happening. And if you know the location of the train at every instant from 0 up until this instant, or past it, I guess, even, and you know the position at every instant after time equals 0, then, it might look something like, I don't know, trains don't really do that, but you know what I mean. What you have here is a mathematical relationship between the two at every time, and then you can start to do math with it. Okay. Okay. So so that's position. We talked about position. I want to say one thing about quantities that have direction and quantities that don't have direction, because in our like everyday speech about, I mean, we basically talk about kinematics all the time. You know, you talk about how fast your car's going or how far you've gone from here to there. But we tend to talk in terms of quantities that don't have direction associated with them. In physics, quantities that have direction associated are going to be a lot more important. And so I want to talk about the relationship between those. So directional versus non-directional quantities. So I'll do it as sort of like a table with directional over here, and kind of like the closest equivalent non-directional quantity straight across from it. So here's the non-directional ones. So the first quantity we talked about was position. That's directional because you can have negative positions or positive positions. Not really a non-directional equivalent of position. We don't have like a sort of everyday language version of position. We just sort of describe the position. We're this far in this direction from this thing. But there's a quantity related to position called displacement. I'll call that d, lowercase d. I'll define that in a second. This idea of displacement is going to be useful in physics. And instead of displacement, we tend to talk about distance. Distance has no direction associated with it. Then the next quantity we're going to talk about is a quantity that has associated direction is velocity. That's lowercase v. The non-directional version of velocity that doesn't tell you anything about the direction something's moving is speed. And then the last one that is going to be important to us, directional quantity, is acceleration. And this is a really confusing one because the non-directional version of acceleration really is acceleration and deceleration. We use this word acceleration, but we use it to have a different meaning than it's going to have in physics somewhat. That's a real shame. That's a shame. But these are the ones that matter to us. We don't care about those non-directional ones very much. So we've talked about what position means. So now I'm going to talk about displacement and compare it to distance. So for displacement, if you define two instants, we'll call the first one T1 and the second one time T2. Then the displacement from T1 to T2 is displacement is equal to the position at the later time minus the position at the earlier time. And yeah, so as I go, when we get to an equation that's going to come up again that you're going to need to use in problems, I'm going to put a box around it so you know to come back to that. So to find the distance traveled between time 1 and time 2, first you have to break up that interval into, I'm going to call it legs, sort of legs of the journey, where each one of these legs, objects only moving in one direction, either positive or negative. So break up the path into legs where the object is only moving in one direction. Then find the displacement over that leg over each leg. And take the absolute value of that displacement. Then add up all these absolute values to get the total distance. Okay, that's sort of a pain, so it's a good thing we're not going to have to use that very much. But let's let me give you an example. So let's say we have a position versus time graph. This is the motion that this object has. So here's the position in meters, and here's the time in seconds. And the object, let's see, 2, 3. Okay, so the object starts, so let's say at time equals 0, think about this for a second. I'm just trying to help you get used to this idea of like looking at these graphs. So say that start at time equals 0, the object is at position positive 1. Okay, so where is there a dot representing that instant? Yeah. So time is equal to 0, so it's going to be, so you know it's going to be somewhere along this. Position is 1 meter, so it's going to be And then second, let's say that at 1 second, the object is at positive 2 meters. So for that one, this is 1 second. The location is positive 2, so the dot's going to be here. At 2 seconds, the location is negative 1. So the time is 2 seconds. The location is negative 1. And then at time 3 seconds, it's at 0 position. So go out to 3 seconds, and the position's 0. And let's say it does something like that in between those specified instants. Okay, so let's figure out first what's the displacement from time equals 0 to time equals 3 seconds. Then let's figure out what's the displacement from time equals 1 second to time equals 2 seconds. And then last, let's calculate one distance. So what's the distance traveled from time equals 0 to time equals 3 seconds? Okay, so for A, to calculate the displacement, we want the displacement from 0 seconds to 3 seconds. So what's the position at time equals 0? So the position at time equals 0 is positive 1. And what's the position at time equals 3 seconds? 0, yep. Okay, so this is 0. And so the displacement from 0 to 3 seconds is the position at 3 seconds minus the position at 1 second. And that is 0 minus 1. And so you get an answer of negative 1, and this is in meters. Anybody have any questions about that? Is that, I think the hardest thing about this is I've sort of thrown a bunch of terms at you and a bunch of definitions kind of all at once. But if you have a position versus, yes.
So this may be a very
Mhm.
why are you taking?
I hope so.
The 3 minus the 1 versus the 1 minus 3, like why?
The displacement is always the later instant minus the earlier instant. Yep, sure. Any other questions? Okay, so And I wanted to say that negative means that this thing over that time, its net motion was in the negative direction. So that's why displacement is a directional quantity. It can be positive or negative, and that tells you which direction it's moved overall. Okay. So the second one, what's the displacement from 1 second to 2 seconds? What's the position at 1 second? At 1 second, the position is positive 2. And at 2 seconds, what's the position? Negative 1. And so the displacement is the position at 2 seconds minus the position at 1 second. And so that's negative 1 minus 2, so negative 3 meters. You can also get positive numbers, but the sign tells you the direction. Okay, so now we're going to do the one that's sort of more tedious. I think there are a couple problems. Yes? Oh, yeah. Okay, so the absolute value is just when you're doing distance. For displacement is the easier one if you know these relationships. Okay, so distance is the one that doesn't have any direction, so we basically throw away all directional information. Okay. Okay, so now we're going to calculate the distance. And for the total distance, I think the easiest thing to do is to draw the path on a number line. And then just measure the lengths of the legs. And then add those up. So let's take this graph and just put it on a number line. So a number line doesn't have any time information included. It just shows where the path that the thing traveled. So 1, 2, 3, let's call this the 0, and then 1, 2. So there's positive 1, positive 2, 3. There's negative 1, negative 2. And the path that the object takes, it starts at position 1, and then travels to position 2. This one is at 0 seconds. We put the times in red here just to keep them. So that's 0 seconds. This one is at 1 second. Then it goes from position 1 down to position negative 1. Sorry, from position. So at 1 second, it's at position 2. And then it goes from position 2 down to position negative 1. So this is at 1 second, this is at 2 seconds. And then the last leg, it goes from position negative 1 to position 0. And that's at 3 seconds. I'll just connect all these. Okay. So if we're trying to figure out the total distance that it travels from 0 seconds to 3 seconds, we just want to come up with the lengths of each. So what are the legs? There's one leg that goes this way, and then it turns around and goes back the other way. So this is one leg, this is the second leg, and this is the third leg. And so we just want to measure the lengths of all those. So this first leg has a length of 1. The second leg has a length of 3. It's going back in the negative direction, but we don't care about that. We just care about the lengths of those legs. So 1 plus 3 plus 1. And so the distance is 1 plus 3 plus 1 gives you 5 meters. So anytime you end up back where you started, the displacement over that motion is 0, because all you're doing is subtracting the two end locations. Okay, so like if you drive from here to Des Moines and back, you've gone a total distance of, I don't know, 500 miles, right? But 400 miles or whatever, whatever it is. But your total displacement is you've gone in the positive direction 200, back in the negative direction 200, and your displacement is 0. Okay, so let's talk about the units of all these things. Position and displacement and distance, although that's not going to be a big thing in this class. Have units of length. And the SI units, that means are meters. So that'll be written with a lowercase m. Okay, so let's, yes? For the distance? Yeah, I mean, you could do it just mathematically based on the values. So if you go back to this mathematical definition that I gave you for distance, so break it up into legs where the object's only moving in one direction, find the displacement of each one of those legs, and then take the absolute value and then add up those absolute values. You can do it that way too. So in this case, that means you would figure out, you could see that it's moving in the positive direction from here to here. So you take the displacement from here to here, which is 1. You take the absolute value of that, which is still 1 because that was positive. Then you go to the second leg where it's going in the negative direction. You take the displacement, which would be -3. You take the absolute value of that, which would be +3. And, yeah, because if you just use the definition of displacement, the position here is -1. The position here is +2. -1 minus 2 is -3. So it's just using all those mathematical definitions. And none of the definitions are very complicated, but I know it's, when you get all this stuff thrown at you at once, it's hard to follow it. But you can, everything I'm doing, you could figure out just from going back to those mathematical definitions and rereading it and then Okay, let's do a problem that sort of combines all this stuff. So let's say a man, well, let me draw a picture. We know it's a man. That's what we know so far. Let's say there's like a house here, and then there's a fire hydrant. That's going to come into it somehow. And then there is his car here. And let's say that between these two, the house and the fire hydrant, let's say that's 15 meters. And let's say between the fire hydrant and the car, that's 10 meters. And let's say the man walks from the house to the fire hydrant, to the car, and then back to the fire hydrant. Let's say each of these takes 5 seconds. Okay. And so now let's say that first we're going to choose the 0 position at the house. A positive direction toward the car. And the 0 time when he leaves the house. And we want to draw a position versus time graph of that whole motion. For the second one, for part B, we're going to just choose some different, those arbitrary things that you have to choose in order to put numbers to this stuff. We're going to choose our 0 position at the fire hydrant, the positive direction towards the house, and the time to be equal to 0, 5 seconds before he leaves the house. Okay, so let's just think through these two. So for part A, I think the easiest way to think about it is to draw a number line and or just draw a line with these locations on them. So let's say this is the house, this is the fire hydrant, this is the car. And we know that no matter what we choose for zeros and positive directions, that's something that's just being chosen by the observer. That doesn't have anything to do with what he does. So what he does in any case is just go from the house to the fire hydrant to the car and back to the fire hydrant. And we know it takes 5 seconds to get from here to here, 5 seconds to get from the fire hydrant to the car, and 5 more seconds to get from the car back to the fire hydrant. Any questions about the way I'm thinking about that there? Okay, so we haven't made any choices about zero position, positive direction, or zero time yet. This is undeniably what happens, and it doesn't have anything to do with choices we make. Okay. Now we're going to decide the positive direction, the zero position, and the zero time. Oh, we're not going to. It was given to us. So for part A, our zero position is the house. So I'm going to say whenever we're at the house, we know we're at that zero position. Okay, that was chosen for us. And then we know the positive direction is towards the car from the house. So the positive is, positive is this way. And so now we can put numerical values on the locations of the fire hydrant and the car. We know the fire hydrant is 15 meters from the house, which is our zero position. So if you go 15 meters in the positive direction from zero, what number are you at? You're at positive 15. And then we know that it's 10 meters from the fire hydrant to the car. That's 10 more meters in the positive direction because the positive direction is defined this way. So what's the numeric value of the car? 25. And as far as times go, it says that zero time is when the man leaves the house. So this is zero time. 5 seconds after zero time, what time are you at? 5. 5 seconds after 5, what time are you at? 10 here. And 5 more seconds later, 15. Okay, so now all we have to do is translate what we have here into a position versus time graph. Okay, so this is the position. This is the time. The times that we're going to deal with are 0, 5, 10, 15. The positions we're going to deal with are 0, 15, and 25. 0, 15, 25. At zero time, the man is at the house. At 5 seconds, the man is at the fire hydrant, which is position 15. No, I skipped one. 5 seconds, he's at 15. At 10 seconds, he's at the car, position 25. And then at 15 seconds, he's back at the fire hydrant. And if you connect these, we don't know what he's doing in between those times, but they connect somehow. Anybody have any questions about that? Okay, so let me do the other one, and I'm going to think about it the same way. I'm going to take this same thing. I'm just trying to emphasize that, yeah. Okay, so I'm going to use this exact same picture I had before. I'm going to take all the labels off. I'm going to start with the stuff that has nothing to do with our choices. Okay, and we've just gone back to what we know happens. Okay, and now for part B, it says choose your 0 position to be at the fire hydrant. So now, anytime the man's at the fire hydrant, we know he's at location 0. And it says the positive direction is now back towards the house. So this is positive. Well, we know the house and the fire hydrant are 15 meters apart. So if you go 15 meters from 0 in the positive direction, what do you get? Positive. You start at 0, you go in the positive direction 15 meters, you're at positive 15. And we know that the fire hydrant and the car are 10 meters apart, but the car now is in the negative direction. So if you start at 0 and go 10 meters in the negative direction, where are you? Negative 10. So now anytime the man's at the car, he's at position negative 10. And now it says that this time, when the person leaves the house, it's already 5 seconds after our 0 time. So this is occurring at time 5. 5 seconds after 5 is 10, so he gets to the fire hydrant at 10 seconds. 5 more seconds, he gets to the car at 15 seconds. And then 5 more seconds, he finally gets back to the fire hydrant at 20. So notice, I didn't change anything about the path that the person takes. He still starts at the house and does this. It's just the labels of everything have changed because we chose new values for 0 position, positive direction, and 0 time. And so let's see what this looks like on a position versus time graph. Okay, so now the times we care about are 5, 10, 15, 20. And the positions we care about are positive 15, 0, and negative 10. And now we're just going to read these pairs of values off of the number line. At 5 seconds, the person starts at the house, which is labeled positive 15. At 10 seconds, the person gets to the fire hydrant, which is labeled position 0. At 15 seconds, the person's at the car, which has the label negative 10. And then finally, at 20 seconds, the person is back to the fire hydrant, which is position 0. And if you connect these up, it looks like that. Because of the different choices of what's positive, what's 0, time is 0, we get this graph shifted this way because of the different choice of time 0. We get the graph shifted up and down because of our choice of 0 position. And in this case, we get the graph flipped upside down. If you look at the two different graphs, they have the same shape, but they're flipped upside down because we chose a new thing to be the positive direction, the new direction to be positive. Okay. Any questions about that? All right, that's it.